Tonight on Bang Goes the Theory, Liz is determined to start a new trend, cow spotting.
Is this move called something?
I'm afraid this is called a sexy mushroom.
Jem enters the space race.
Dallas! He's made it!
And I'm going to control your mind just by flashing up a few fivers. Amazingly, the group that handled the money ate 50% more of the sweets. Hello and welcome to Bang Goes the Theory. Now, a bit of a weird one to kick the show off this week. Apparently, cows like to stand north-south.
Yeah, or south-north. It's all about orientation.
Exactly. Well, a group of German and Czech scientists have studied satellite photographs of 8,500 cows from across every continent.
Well, except Antarctica.
Exactly, except Antarctica. Anyway, the upshot is apparently cows have magnetic qualities.
They do indeed. Now, this is not quite as weird as it may sound, because apparently a lot of animals and even plants are affected by the Earth's magnetic field. Now, I'm not really into train spotting, never have been, but you know what else? I'm all over this like a rash. I'm going cow spotting.
Geek.
My aim is to find out if cows really do align themselves in a north-south direction when grazing. Seems a little unusual, so to investigate, I've decided to employ rather unusual measures. Meet mistake number 1, the Robinson R-44 helicopter. Meet mistake number 2. Known simply as Q, Quentin Smith is no ordinary pilot. He's the former world helicopter freestyle champion and the man I've rashly recruited to fly me above cows. The idea was that we'd find a field of cows, I'd take photographs of them and analyse which way they were facing.
I do know one fact about helicopters and cows, though. Is it true that if you can see the legs of a cow from a helicopter, you know you're around 1,000 feet up in the air?
Yes,
Is
exactly.
it? Excellent.
And sheep, 500 feet.
500 feet. So if you can see the legs of sheep, you know you're 500 feet. What about horses then?
Much longer legs, 1,500 feet.
Excellent. We don't need any of this gizmo.
No.
We soon found what we were looking for, a dairy herd.
Madam, Liz, some cows.
Moo cows!
Here's our aircraft aligned north-south.
Perfect, Q. That's great. We're aligning ourselves very nicely. Ready to take some shots?
Amazingly, some of them were actually lined up. But then we looked at the adjacent field.
They're all over the place. I can't really tell if anything's aligned.
In the end, I obtained photos of 221 cows. It was time to head back to Bang HQ to analyse them. But just as I thought we were going to land, Q figured a lesson in the wonders of helicopter aerodynamics was appropriate.
Q, why are we going backwards?
Well, it's what helicopters do. Backwards, forwards, any way you like.
I didn't sign up for this. Are you going to start showing off now? Is this move called something?
I'm afraid this is called a sexy mushroom. We can just do it
You're
around the
joking me.
A little bit of rotating like this. So I'm just going to wind the engine out slowly and auto-rotate.
What do you mean, wind the engine out?
Well, we don't need an engine in the helicopter, only for going up.
Right, you're going to do it?
Yeah.
Okay, just do it.
The engine is in neutral and the rotors are only spinning because of the air rushing through them as the helicopter falls.
Now you're really freaking me out. This is unbelievable. No engine and we come crashing to the ground. Q, what are you doing to me?
It's called auto-rotation.
That actually did feel quite cool.
I like your pilot.
Do you know?
And I suspect he likes you too.
Let's get on with the science now, shall we? Here are my results.
Yeah, and what are these lines about?
Okay, so this is like head to tail, tail to head, just to show the orientation of each cow, right?
And if I just saw that photo, I would be completely convinced.
That one's not bad, yeah. The only problem is, the very next field, they were pretty much all over the place.
It's just a bit random.
Yeah, or most of them were actually aligned east to west for some reason, or lying down.
Yeah, but the impression I got was this was a pretty brief snapshot in time. You guys weren't up there very long.
No, we weren't. I mean, it doesn't make our results statistically significant, that's for sure.
No, but we don't give up that easily.
Oh, no, we don't.
So what we decided to do was monitor the cows for a longer period of time and take into account things that might affect them, like weather. I've created this. The Moo Monitor, a device that contains a digital compass, can reliably and regularly record bovine movement, and of course, be humanely attached to a cow. All I need now are some willing volunteers. These tags will record our miniature herd's position every 10 seconds for a month. Basically, for the next 4 weeks, these guys aren't going anywhere without us knowing. All I need to do now is figure out how I'm going to attach the tags to the cows. And for that, I will need the help of a seasoned professional, Farmer Barnes.
Hello?
Oh, there goes a volunteer. Let's push them down on there. Hello there. They can't scratch up here, can they, too much?
I wouldn't have thought so. Yeah, you don't see cows running around like this here every day, do you, with a jobby on the top?
There is another factor to think about. On a windy day, the cows may well face into the wind. On a cold day, they might want to keep their sides pointing to the sun for warmth. This weather station will monitor what the wind and sun are doing, so we can discount the cold and windy days.
Yep.
Go on. Come on. Whoa! That's it. The cows are now out in the field. The monitors are on, recording every direction they're looking. And we get to find out if cows have an internal compass or if Liz's story is a load of bollocks. And the results were genuinely interesting.
Okay, explain.
If you look at the plot here, you'll see the cows did face in a southerly direction for most of the time.
Okay, so that's in concurrence with the original research, right?
Right, but the wind was also blowing from a southerly direction, so we don't know for sure whether the cows were just facing into the wind or were affected by the magnetic field.
Now, that's all fine and dandy, but why is this important?
Well, it's important because scientists are getting more and more interested in why and how the Earth's magnetic field affects mammals, and they even think it does affect us humans as well.
But there's one question you haven't answered.
What's that?
How does a helicopter fly if you've turned the engine off? I don't get that.
I'm
You know what I
absolutely
mean?
with you, Dallas. I was thinking the same thing, and by the end of the series, I will know that.
Good man yourself.
Watch this space.
Space. Space, who said space? I love space.
Oh, here we go again.
Coming up next for you, we have got a space anniversary, but possibly not the one you're thinking of. Now, it's a story of incredible courage, and it's a story that we want to remember here on the show.
This footage from 1960, almost half a century ago, is of Joe Kittinger floating up in a balloon to just over 100,000 feet, and then calmly jumping out. On his freefall descent, he reached speeds of over 600 miles an hour, and he still holds the world record for the highest skydive. And to celebrate his achievement, we thought we'd have a go.
Kittinger almost died in the attempt, so for this, we needed a man of action. We needed somebody who could laugh in the face of danger.
You are absolutely right. We're going to need Mini Dallas from last week. For me, there's two incredible things about Kittinger's mission. One, he parachuted back from space, and two, he went there in a balloon. And it got me thinking, how high do you reckon a helium balloon goes when you let go of it? Well, in theory, if it's less dense than the air around it, it'll keep on rising to the edge of space. But there is a problem. Down here at ground level, you've got the full weight of the Earth's atmosphere, and that squeezes this balloon, keeping it in the shape that it is. But as the balloon rises, the weight of the atmosphere gets less, atmospheric pressure gets less, allowing the balloon to expand and expand until it bursts. And that's our first challenge, getting the right amount of helium in the balloon to get it to the edge of space, but not so much that it explodes on the way. The next thing that's going to cause problems to any space engineer is weight. It doesn't matter if your spacecraft has NASA written on the side of it or bang. Keeping the mass low is the key to waving Earth goodbye. Spacecraft need to save weight, and for that they usually go for the most exotic alloys and composites available. I'm no different. I've gone for a step growth polymer, or polyurethane insulation foam as it's known at the local builder's yard. Now the thing with this stuff, it's an amazing insulator, but it's not very strong. And luckily for me, it doesn't need to be strong, because all it has to do is get a lightweight doll and a couple of cameras from here to the edge of space. That doesn't mean it's a walk in the park. We'll take off at around 20 degrees C on a nice summer's day, but then things are going to change pretty fast. There's almost no air up there, and the temperature drop is deadly.
By using a plastic Dallas, we neatly avoid the cost of a funeral, but we can't get round all the problems caused by temperature. You see, at 50,000 feet, the air temperature is down to minus 50 degrees, which is why I'm here in an industrial freezer. The problem lies with the electronics. Batteries don't like cold temperatures, and these cameras here, they're designed for maybe -5 on your skiing holiday or 30 degrees on your trip to Benidorm. So we have to test if the batteries in these things are good at -50.
The coldest point will be near the top of the troposphere at around 60,000 feet. Above that, Dallas will be in the stratosphere, and the temperature will eventually begin to rise again.
Okay, that's about 5 minutes. Battery's still working. Dallas, have a little look at yourself.
All we need now is a very large balloon. A mate of mine, Steve Randall, who's designed the electronics, and with the aid of some string and tape, we have ourselves a space mission.
The first Campbell in outer space. I'm loving the sound of that.
It is just the edge of space.
That's good enough for me.
And he hasn't got there yet. We'll find out how little Dallas gets on with his mission later on in the show.
OK, time to move on. Now then, here is a question for you. How gullible do you think you are? Because recent research seems to suggest that we're incredibly prone to the power of suggestion. We just can't help ourselves. Anyway, we have set up an experiment to put that to the test. So I'm a pretty decisive person. I make my own decisions. I understand the reasons why I make the choices I do. Or do I? I mean, does anyone? I want to see if we can change the way people act without them realising they're being manipulated. We've asked members of the public to take part in a series of tests which are being run for us by psychologist Peter Naish.
So, nothing nasty to do, so hopefully you'll be happy to stay right the way through.
The participants are given a one-handed counting task.
Ready, steady, go.
They're told we're looking at left and right-handedness, but this is just a front.
Now,
A second group of similar volunteers do the same test, but instead of boring old bits of paper,
this is where we get you to count a pretty large pile of money.
they get to count real banknotes. This is the only difference between the two groups. Let's see if that small difference can affect their behaviour.
Now, we're going to give you some sweets.
We've asked both groups to compare 2 bowls of sweets.
What we want you to do is say which you find the most chocolatey, the most crunchy, and so on.
Given 10 minutes to make their decisions, something rather interesting emerges. On the left, those who counted paper only eat enough to answer the questions. But the people who counted money just kept on eating. Amazingly, the group that handled the money ate 50% more of the sweets. It seems money can make you hungry. This effect is called priming, influencing a specific behaviour without the person being aware of it. But how can money have an effect on hunger? Well, money seems to trigger an innate desire, and in many ways having money is the same as having resources. And back in the dim, distant past, resources meant food. Money and food are linked by the same basic urge to survive. You could argue that it's not that hard to change someone's hunger level. But my psychologist friend Peter tells me we can also change how people treat each other, again without them realising they're being manipulated. I have to see this. First, we reinforce the priming. Both groups get an identical word task, except that, for one group, the words are related to money and wealth. Then, we secretly film them and watch their behaviour. As my friend struggles with a pile of papers, some of our volunteers stop to help her. But not everyone feels the need to help. Guess what? Those who handled the money are more likely to keep on walking.
Oh man, that's really bad.
I'm an awful person.
No.
It's not that they're simply being unhelpful. Psychologists have studied this and found all kinds of subtleties. It just seems that money makes you more self-reliant. And self-reliant people expect other people to be self-reliant too. Our primed volunteers don't think my friend needs help with her drop papers. Money doesn't just change the way we feel about people. Apparently, it changes the way we feel, full stop. So we're going to test that out here with a little ice-cold torture. That's really painful. Right, it's time to see if our money priming has changed how much pain our volunteers feel.
Yeah, it's a bit nippy, isn't it?
Yeah, quite painful.
There's no pressure, you can take it out whenever you're ready.
Yeah, I think I'm going to have to...
This is incredible.
Okay, well done.
As a group, those who handled the money are coping in the icy water for twice as long as the group who handled the paper.
If I stood here for an hour, would you kind of call an ambulance or something?
Researchers think that the reason for the pain-reducing effect of money is again due to psychological links. Money equals power, and power equals physical strength. So, we've seen money affect hunger, helpfulness, and pain thresholds. But could all this just be a coincidence? Well, yes, there is always that possibility, but several other studies have had similar findings. And a bit of number crunching on our own priming results show we can be 98.6% sure it was no fluke.
They were pressing the right button in your brain, you didn't even know. That's scary.
So the moral of the story is be careful who's messing with your mind, because you might not always be doing things for the reasons that you think you are. Incredible.
That is so interesting. Imagine all the things that happen to you every day that might just influence your very next decision. That's a bit scary.
I think it's deeply scary, but there's so much we don't know about human behaviour. In fact, recent research has shown that if you spend 10 minutes imagining that you're a professor before you do a pub quiz, you'll actually do better.
No way, that's brilliant.
I'm going to try that out, definitely.
Oh, and now don't you try and influence me now that you know all about this stuff, okay? Because it won't work on me.
Look at my pencil. Imagine the
Get
think
away.
about pencils. Think
Shut
about
up.
nothing but pencils.
Okay, it's now time to catch up with Dr. Yan, who hits a high street near you every week to teach you lots of great sciencey stuff.
Oh no, but someone's only gone and given him some fireworks this week. That's got to be a mistake.
We all know that fire needs heat, fuel and oxygen. So how does rocket fuel burn in space when there's no oxygen around? The answer is that rockets in space burn because they take their own oxygen with them. So just like a diver going underwater with an oxygen tank, they've got their own oxygen. Inside this rocket is packed the equivalent of a balloon full of air. How? Gunpowder. And gunpowder contains fuel, that's carbon and sulfur, but also potassium nitrate. And potassium nitrate contains oxygen. Lots of oxygen. So in theory, I could set off this rocket on the moon. I don't think we've got the budget to do that, but I can show you it burning somewhere else where there's no available oxygen. I'm going to set it off underwater. Right. go. Works underwater. So that's how rockets work in space, and also why you shouldn't try and put out fireworks using water.
Right, now to catch up with Mini Dallas and his mission to become an astronaut.
In 1960, NASA spent millions getting this man, Joe Kittinger, to parachute from the edge of space. Now we are mounting our own near-space mission, Operation 500, so called because that's what it's costing us. All we're using is a bit of foam, some high-street video cameras, a lot of help from this man, electronics expert Steve Randall, and a very big balloon full of helium.
This is what we call the payload. So the balloon is going to be lifting this into space. These arms, they just serve one purpose, and that's to hold the cameras. The cameras have to be out here, just so that they've got enough distance to focus on Dallas down below. And when we send them up in space, these are what's going to record the journey. This is ready to launch now. We've got to go. Steve, you ready?
Yeah, we're ready.
3, 2, 1.
And Dallas and his helium balloon are heading off to the edge of the atmosphere. All we have to do is keep up with him on the ground.
Well, little Dallas is on his own now. Now, just like a proper space mission, all the data is broadcast down onto a computer here on Earth. That then can monitor his altitude, his latitude and his longitude.
At just a few hundred feet, little Dallas encounters his first barrier, dense cumulus cloud. It might fog the lenses, but it won't slow his ascent.
Just right now, he's pretty damned high. According to this, we're at about 30,000 feet. That's the kind of place that aeroplanes fly.
At this height, there is a risk we could encounter a jet stream, a narrow band of easterly flowing winds that could hit 200 miles an hour and blast us out over the North Sea.
Where he is now in the upper atmosphere is actually the coldest that little Dallas is ever going to feel, minus 55 degrees. But luckily there is good news. As he goes higher, he's actually going to get warmer because he's going to start collecting more of the sun's radiation. Wow, the balloon's now gone over 50,000 feet. That's out into the stratosphere there.
Right now, he's at 94,000 feet.
So it's pretty much into space as we speak.
We've done it! 100,000 feet, and the curvature of the Earth is clearly visible. The onboard computer is set to release little Dallas and his parachute at exactly the same height as Kittinger, 102,800 feet. Unhitched from the balloon and with almost no air resistance to slow him, Dallas hurtles back to Earth, accelerating until, like Kittinger, he reaches his terminal velocity at around 600 miles an hour. At that point, after an incredible journey, the batteries run out.
We're searching now for where we anticipate Dallas to be landing. And a worst case scenario for me is that he lands in a populated area. Things from space should not be dropping on human beings.
The last contact we had with the Dallas doll suggested he might be heading for the town of Chatteris in Cambridgeshire.
For all the planning, design and weather surveillance that's gone into this,
It's come down to the fact that we're looking for a 6-inch doll dressed as an astronaut. And after 2 hours of searching,
Come here, come here, come here.
Dallas! He's made it! Dallas, you're now an astronaut. He's made it! And here he is.
Oh, seriously, that was so amazing to watch. I mean, it's probably my favourite film so far.
I have to say, I feel really emotional about it. I'm living my astronaut dreams vicariously through a doll. How long did it actually take to get up and all the way back again?
It takes a couple of hours to get up to space and probably only about half an hour to come back down to Earth.
Now, I don't mean to be picky, but you know they say in space no one can hear you scream. Like watching that film, when he falls down, you can hear this whistling noise, this sound. So what's going on there?
I know, it sounded a bit like poor little Dallas weeping, but actually at 100,000 feet there are still a few molecules knocking around the atmosphere, right?
Yeah, that's right. And at 600 miles an hour, like little you were, you knock into enough molecules to create sound waves, and that's the noise you hear. It's not a scream.
Amazing. On that truly heroic note, it is time for us to go this week. Can you say goodbye, please?
Goodbye, please.
Bye.
Bye. Guys, I'm really not happy about this. Seriously.
Dallas, don't worry about a thing. The doll was okay. You made the right stuff. You'll be fine.
Dallas, I think you look dead cute. Are you ready? 3, 2, 1, go!